Hi everyone. Today we are going to discuss about how to model pin diodes. Pin diodes are something like a switching models, mainly to turn one path on off for some certain applications. One is reconfigurable antennas and phase correction circuits. Many places you can see the pin diodes. So we'll see how we can simulate pin diodes in HFSS. Uh, The main challenge in front of us is we cannot simulate diodes inside HFSS 3D because diodes are nonlinear devices, so Maxwell equations holds goods for passive and linear systems. So these are nonlinear devices. So let's assume this is my pin diode and which is a non-model here. I have a transmission line and bottom I have a ground. So in between this gap, I need to connect a pin diode and make the circuits continuous. That is my intention for this work. Uh, there is one more video we are planning to create for an antenna case where you don't have a proper ground. So these two cases are uh, need some understanding how we need to simulate it. What we will do for the time being is I'm just disabling this guy. What you can see over here is there is a port 1 from this transmission line and it's going to end at port 2. And what I created is I created two more additional ports. You can see uh, this is the two ports where we can connect diodes. And on top of that there is a radiation box. That is the only setups. There are two ways we can simulate diodes in spin diode in HFSS. If you consider one paper, okay, this is a antenna reconfigurable antenna using pin diode where you can extract the RLC, so LC combination, and you can see the capacitance resistance combinations varies with the two conditions, either with the 8 either with the on and off condition. You can see at off condition it is giving almost like a 15 kilo ohm. When it is on, it is giving 3 ohm resistance. Okay, and a high frequency rather than the resistance, the reactance part also plays a role on the blockage of RF. So you can create RLC boundaries in HFSS and then simulate it. Otherwise, what you can do is you can do a combination of HFSS and circuit. So circuits are the tool where you can combine both passive and uh, active circuits. Means you can the circuit can contain HFSS models and diodes, amplifiers, and everything, and then you can do a system level analysis. So I'll do an example. I just inserted a circuit. Then what I'm going to do is I'm just drag and drop this HFSS into this. Okay. So what you're going to see is that HFSS model has comes inside the circuit by just drag and drop it here. So you just expand it, make sure the sweep, the S parameter is selected under this. And what you need to do is I just going to create a two ports, and this is my port, and instead of creating RLC boundary in HFSS, I can create RLC boundaries here. I just put a capacitor, then if I want I can just type inductor, place an inductor, and if I put one resistor, put a resistor. And if you want more details, you can go into this uh, second tab, and under the capacitor different types of capacitors are there. You can add more temperature dependent capacitance models and many other things, and see coaxial cables, there are a lot of diode models. Diode model means diode having lot of parameter you can input here. Okay, so this is the simplest way. You can just type or make a wire connection between this, and what you can do is select the other wire and connect it here. Okay, so what you are going to do is you need to give the RLC values which is equivalent to the on and off cases. Okay, I believe I already modeled this particular circuit. Okay, so same thing, port 1, port 2, RLC, everything is connected here. And in this port, what you can do is you can make it as a microwave port and click OK. You can see microwave port loaded with a 50 ohm, and over here you can also make this as a 50 ohm. And here both you will get both S parameters between port 1 and port 2 if you are running the analysis. But the problem is, let's say I wanted to calculate the voltage or the signal which is passing through this one, and I want to see what is the voltage inducing here or coming back to the port 2. That you can control it by just double clicking here, go to edit source, and you can set voltage or power source. Okay, and put a sinusoidal, go to add selected port. Here let's say I want to apply 1 watt power. So if I want to put 1 watt, just put a 20 into SQRT of 1. Okay, so this is a conversion method. This is actually you need to give a voltage here. So if you want to give in terms of a watt as a 1 watt or something, what you need to do is just convert in multiply into 20 into square root of 1, and this is valid only for a 50 ohm systems. And if you click somewhere, it is equal to 20 volt, and it is nothing but it's coming from our normal equation. Voltage is equal, power is equal to V square by R, where R is 50 and voltage is your RMS voltage, and voltage which you are going to give here is peak to peak voltage. Okay, this is a 20 volt peak to peak, so it will have positive 20 volt and negative 20 volt level. So this is the settings here. Now if you see here, you can see there is a source also included, so that 20 volt will go here and come back here. That is what going to happen. Now what you need to do is you can just right click here, add an Xing solution setup, linear network analysis. So one linear network analysis I already added here. So it is you can see the frequency you can specify. Just click over here, or else you select it and edit it. Okay, and you can say I need to see from 1 to 5 gigahertz counts, add it, and just run it. So here you can see the L inductance value is 0.15 nanohenry and 50 kilo ohm and 32 femtofarad. This is a case when the diode is in off condition. Okay, and click analyze it. Usually the simulations with the circuit can be completed in couple of seconds, even sometimes fraction of seconds. And right click over here and go to rectangular plot. As usual, 4 port now reduced to 2 port, so you can see the S21 between the two end of the microstrip line when the diode is off. Just click new report, you will see the S21 is very low, okay, when the diode is off. And okay, so one more thing is I also wanted to see if I put a off condition, how my field is going to propagate through the HFSS. So I can send the information which I ran in circuit back to HFSS by selecting this guy, right clicking, and do a push excitations. So the voltage and magnitude and the phase of the voltage will be pushed back into HFSS, and you can see here under the design, this was the HFSS design, and you can see under the excitations on the edit source, this magnitude and phase all for all the ports are updated with the circuit data. Okay, and if I do a field plot, let's say I'm going to I want to see the field through the system, right click and plot fields, go to Mac E. You can see that field is going only up to this point, and beyond that fields are not moving at all. And you can do the animations and just doing quick animations for you. So you can see when the diode is off, the fields are not going moving through this. And here the advantages are you have reference the same ground plane at all the places. We will next discuss about if that is not, there is no ground plane. And that this point also we will discuss in the second video. So going back to my circuit, I'm going to put instead of 15 kilo ohm, I'm going to change this into 3 ohm and 32 femtofarad I'm going to change to 8 femtofarad. So an advantage with the circuit is you are only simulating once in HFSS, and circuit simulations are very fast. In couple of seconds you can simulate on and off case. Let's assume you have a very complicated HFSS model, may take 1 hour or 2 hours to simulate it, and this one we can do much easier. So you can see when the diode is on, the S21 is quite good. It's lossy at a very high frequency, but it's quite transmissive at this frequency. And if I do go back here, I wanted to see the field propagation when the diode is on. Right click here, do a push excitations one more time. And I'm fine when I'm going back to my HFSS after the push excitations. In the HFSS design 2, you can see now the field is propagating to the other side, and you can just see the plot animation. So you can see field is going to the other ports. So this way you can club both HFSS and circuit simulations. So one thing, this here the diode on this paper, they have used this particular diode for the simulation. So how I can get more accurate simulations? What you need to do is go and search with this parameter in Google. So I did that search and I will show you some of the things. This is a this is a website, so you have to go to that particular website. You can get a lot of information, so you can get the data sheet, you can get the application notes. If you go to application note, they gives about how what is diode, what are the parameters, how to how the the equivalent circuit of that particular diode will look like, and what is the value of the equivalent circuits, and it will give you how a diode has to be modeled. Okay, if you want, let's say this is your antenna or system, and if you want to connect a diode, you need to have a VCC and then an RFIC which should block all the RF signals. So if you want to connect it in series, this is a way. You need to have a DC blocking capacitor at these two sides. It will make sure the DC signal for biasing the circuit will not goes into the load or source side. So the signal, the DC signal will comes here, will go through this way and come back to the ground, and there should not be any RF signal should goes to the source side of the power supply. So the signal will RF signal will go only through this way, and this is for the shunt side. This should be the circuit. So what you need to do is, in order to get a proper circuit, proper working instead of RLC, most of the diodes will have a different behavior with respect to the biasing voltage, and its performance also varies with respect to frequency. So RLC is the simplest optimize you can say simplest way of representing a pin diode in on and off cases. So more accurate things, what you need to do is you need to go to this site, and there is a designer info. If you click over here, it will download a bunch of files. It's called S parameter file. Okay, if you open this H parameter file, you can see When diode, when 0 volt is applied, when 1 milliamps applied, 1 milliamps applied, 5 volt applied, and when this is with the 10 milliamps. So different conditions of a diodes are given as a S parameter. So S parameter is nothing but if you measure it across a diode in a transmission line and proper de-embedding is done. So this will be the working of a diode at a different conditions. So what we can do is we can use this as a condition for 0 or when diode is off, and this can be used as a diode is on. That will be the most accurate way. So I will show you how we can import that kind of a S parameter models into the circuit. Just have to go here, remove this part. So this is the part where we were trying to remove it, Control X, and paste it somewhere here. Okay, and we can say I don't want this guys, so right click, deactivate. Oops, sorry, everything. Otherwise it's not necessary to deactivate everything, you can leave it like that also. So over here I need to bring that S parameter into circuit, and what I need to do is S parameter will comes under this one, input models. Go to input. Okay, then it will ask where that S parameters are. So I already copied that S parameter under this particular folder location. Copy that and paste it over here. And I am going to import my S parameter when it is off case. Okay. And I am also going to import, because why we need to import multiple times. So I am just going to import one more time. This is my 5 volt case. So one for on case and one for off case. So just put it for the off case and connect to here. Okay, and run it, analyze. Oops, there are some issues. Reduction 2 points. Hello, I find out the reason for that error. Why? Because this S parameter model was just left open. So we need to deactivate the S parameter for the time being. If you are not using, just try and right click and analyze it. So this will be the case when the diode is in off condition, and you can just go here and check. So this is the S parameter. When you are using an ideal S parameter value, you will get a maybe very smooth S11 or S21, but when you are using the actual model, you can see the ripples which is coming up. And we can just cut this one, paste it somewhere here, take this one, paste it here, and make it active, and this one make it deactivate. Okay, I'll leave it like that and analyze it. So this is a case when the diode is going to be on condition. See how the S parameter change. Oops. So there is a correction in my S parameter. This S parameter is this S parameter with the 5 volt is not with not for a diode on case. I believe maybe uh, maybe reverse voltage or something. So what we are going to do is, instead of that, we are going to take the S parameter model, which is given as 10 milliamps. Okay, so over here you can just go here, take this and put that 10 milliamps S parameter model here. So port 1 and port 2, you can connect it, right click and analyze it. Here you can see that S parameter. So you are getting that S parameter which was pretty similar when you are using RLC, and S parameter, when this S parameter you can see some ripple, and this may be a measurement ripples which has introduced as a noise in this. Okay, so like that there are two ways. You can either use RLC boundary or use S parameter from the manufacturer side. And Let's see how we can simulate antenna kind of a problem and see the antenna gain and everything in the next video.